Hey guys, this is continuing the study guide on static fluids. I'm on page 25 of the study guide. The bottom there. Okay, now whenever something's in a fluid, partially or totally submerged in a fluid, it is said to have a buoyant force. Buoyant force is like normal force, which is a hard surface pressing up against an object that's on it, normal force. But when you're in a liquid, we don't call it a normal force, we call it buoyant force. And I like to just call it BF, but AP outline equations, it calls it F subscript B. Okay, BF is pretty big. If you had an object that's floating, let's say a boat, okay, only part of it's underwater, and that part underwater is experiencing an upward force called the buoyant force. And if you're floating, you should realize that the floating force, the buoyant force has to be equal to the gravitational force, which I just call weight, little w. Okay, so whenever something's floating, the buoyant force is equal to the weight. I hope you remember that weight is equal to m times the acceleration due to gravity, or we call it the gravitational field. Okay, so you should remember that as well. Okay, so that first example, 30,000 kilogram ship has what buoyant force acting on it if it's afloat? Well, you should realize that kilograms is mass, and if it's floating, the buoyant force is equal to the weight. The weight is equal to mg. So it'd be 30,000 times 9.8, but I just used 10 in AP Physics. So that'd be 3 times 10 to the 1, 2, 3, 4, 5 newtons. So again, when something floats, what two forces equal each other? Yeah, the weight and the buoyant force. Okay, let's keep on going. Okay, Archimedes or Archimedes, ancient Greek thinker, and what he discovered was that this buoyant force is equal to the weight of the fluid that gets pushed out of the way. So if I could weigh this amount of water that got pushed away by the boat, I mean, that would weigh the same as the weight of the boat or the buoyant force. Okay, so buoyant force is equal to the weight of the displaced fluid. That's the best way to say it. Okay, so looking at this picture, this cartoon right here, this fish is basically floating. They have a swim bladder that controls their density so they can float, just stay there at some level. You can see that the buoyant force would have to equal the weight. Same with the other fish. Now this guy, I don't know, this guy's underwater. And you can see that the weight is greater than the buoyant force. Therefore, he's accelerated to the bottom of the water, and they didn't draw the one force that's missing now that he's on the bottom. And that force would be what? Upward force. This upward force plus this buoyant force would have to equal this weight right here. What do you think that upward force is? Yeah, normal force. Okay, that would be Fn if you want to call it that. I just call it normal force, or capital N. Now you don't have a normal force when you're floating because you're not on a hard surface. Okay, so we can say that, I'm going to use my terms, okay? N plus BF is equal to the actual weight. Now, N is called the apparent weight. If you ever went fishing and you catch a fish, let's say, and the water makes the fish feel lighter because in that case, it would be tension though, in the string. The tension would be acting like the normal force. So I'll get into this later, but let's say here's a fish that you caught on a string. Here's his weight, and here's his buoyant force. And the tension is acting like the there's a fish you caught. Okay, so tension plus the buoyant force would equal the weight. So you can see that the tension would be like the normal force, the apparent weight. The fish will weigh not so much. When you take him out of water, he really bends your fishing rod because the tension is no longer, I'm sorry, the buoyant force is no longer there. So let me write it like this. So the apparent weight will increase, if you have tension, if you have buoyant force, the tension won't be as big as if you, I'll get back to that, okay? Okay, so let's explain why you have a buoyant force in something that's submerged partially or completely in a fluid. Well, we just learned before that there's force on that submerged object right there. There's force on it because of the molecules hitting it in all directions, the water molecules, the fluid molecules, and the air molecules pushing on the water. Anyway, you already know that the pressure here at that level and the pressure at this level, what do you know about those? Well, pressure 2 is greater than pressure 1. Remember, pressure is equal to HdG, where H is the depth. So P2 has it's deeper in the water than P1. So pressure down there is bigger than pressure on top. You also know pressure is force over area. So the force, if the area is the same, the pressure is bigger because it's deeper. area is the same, right? But if the pressure is higher, the force is higher. So there's a bigger force on the bottom due to water molecules hitting it than on the top due to water molecules hitting it. So if you take the net force from those two forces alone, you get what is called the buoyant force. Okay, how do they do this up here? So the buoyant force is equal to net force. F2 is positive, F1 is negative, so you add those. F1 is negative because it's going down, if you want to do that way. Okay, then right here, they just changed it to using this equation, F equals P times A, right? Okay, and right here, they use the pressure equals HDG equation using the two different heights, H1, H2. Not really heights, but depths. Okay, so then they, as you can see, they just distributed out common terms. Again, that looks like P. What does that symbol stand for? Density, right? Rho stands for the density. So they took the density of fluid. We're assuming it's incompressible, any fluid, so that the density is the same deep in the water as it is on top of the water. It's not the density that changes, it's the pressure. Okay, so that's kind of confusing. They look like the like pressures. Okay, then, well, that's pretty cool. A times area times height is volume. So let's see, so we're talking about the area, I guess, above this thing. That's the surface of the water. Oops. Okay, so that chunk of water minus what? EGH. Okay. Oh, that would just be, okay, the way they do this, H2 minus H1, that would just be the volume of the block, right? Because it would be, the area would be this face right here, that's what we're talking about, or the bottom face, the same. H2 would be right there. H1 would be there. So we're talking about the area, the volume. We did this equation right here. We're talking about the volume of the block. The volume of the block, or the volume of displaced fluid. So basically, here's Archimedes' principle right here. Buoyant force equals dVg, density times volume displaced of the fluid displaced times g. That's on the equation sheet in that blue box. And the thing is also, Archimedes said, well, density times V is the mass of the, right? D equals M over V. So M equals dV. This is where people get mixed up. So density times V is equal to the mass of the fluid, not the density of not the mass of the box, not the mass of the box, or the object submerged, but the mass of the fluid. So it's very important to get this distinctly right. So if I let me write in my terms, BF equals dVg. That's how I do it. Okay? It's very important, very, very important to note that this is the density of fluid, not the density of the object. In volume, it's the volume of the fluid that's got displaced, or the volume of the object that's underwater, or partially underwater, or whatever liquid it is. So that's one that can be both of the volume can be the characteristics of the displaced fluid, or the volume of the object that's underwater. Excuse me. Okay, so important for you to know that. Here we go with the equation again. This is always true, whether you're floating or if you're submerged, or even if you're on the bottom of it. Okay, that's the weight of the displaced fluid, not necessarily the weight of the object. Okay? Usually it's not the weight of the object, so don't get that mixed up. If something's floating, then it would be, FB would be the mass of the object times the acceleration due to gravity, 10. But if it's submerged totally, no. That's just what the buoyant force is. Buoyant force would be not the mass of the object times g. The weight could be less or more than the buoyant force if you're totally submerged. The weight of the object. But, excuse me, in all cases, the buoyant force is equal to the weight of the displaced fluid. You should memorize that. And there it is, right there. Okay, my thing is stopping. Hold on. If you keep on falling down, I have to reshare this somehow. Okay, sorry. Let's try it again. It's being a poopy head. Okay, so you can see right there, the buoyant force is the weight of the displaced fluid. You need to know that without a doubt. Okay, so we're going to do some AP type questions here. But I think I'm going to save that for the next video so you can take a break here. Because these go on and on. This gets rather complex. So I'm going to say, let's end this video for now. At least you got the concepts there. We'll come back another day and do some of these problems. Okay, have a good night or good afternoon.